Hello everyone. We are going to start quantum cryptography today. This is a new chapter and we are finally getting into quantum computing and quantum information. Till now we have been talking only about the language of quantum computing, that was quantum mechanics, and learned some basic ideas and some phenomena. But now we will focus on specific topics on quantum computing, and one of them is quantum cryptography. So, in the modern world, cryptography is a very important thing in quantum because you have to make sure that your information is secured, and by the end of this chapter, you will see that the power of quantum computing can enhance your security like exponentially. All right. So, but this is a huge area of research, and there are many ideas uh, that that is floating around, and people are trying to make uh, more cryptographic protocols that are extremely difficult to break. So in this course we will just give you a basic idea, and one of the famous protocols called BB84. So we will talk about it in details in the upcoming videos. So in this video I will just give you a basic idea of what quantum cryptography is. All right, so let's start. So first, if you're doing quantum cryptography, so that means that you will use quantum computers. That means that you will use qubits. All right, so we have already seen that a received state, a received unknown quantum state cannot be reliably identified unless it has been promised to be in a specific orthonormal state so the receiver cannot reliably read the message. So what it means, let's say I'm trying to send some messages through some states, and if they are not if they do not belong to a specific orthonormal set that you have already learned in the last chapter, that you cannot reliably distinguish via some measurement. All right, so the message that one party is trying to send to the other, the receiver cannot reliably read it. Okay, that is a problem in quantum when you're using quantum states. So we have to keep that in mind. Secondly, B, that any attempt to read the message destroys sum of the information, right? Because you know that if you want to do a measurement, then so by reading it means that you will do some measurement of the state, and if you are doing some measurement, then it will collapse to one of the eigenstates of your measurement, and then if it is wrong, then you cannot trace back to the previous state because the measurement is not a reversible process. All right, so these are the true fundamental drawbacks when you're doing quantum cryptography and you're dealing with qubits. But actually we can use it in our advantage. Let's see how. Let's say that there are two person, Alice and Bob, who wants to communicate, and they're sending qubits. All right, let's just draw a cartoon picture, and they're sending it. Okay, and there is an eavesdropper who is, let's say, Eve here, who wants to read their message, and they want to, and Alice and Bob wants to keep it secret, but Eve wants to read it and keep it intact, so that what Eve wants actually is she wants to read the message, but she doesn't want others to know about it. All right, so the advantage here is that whenever Eve tries to read it, it will collapse, and because of the no cloning principle, she cannot clone it in general, right? You will have a string of qubits, so she cannot clone arbitrarily any qubit, right? As you have learned from the last chapter. So whenever Eve wants to do any kind of eavesdropping, that means she wants to read the message, then there will be some trace in the system, and and we can use that thing for our advantage. All right, so this says that number B can actually be used to our advantage. All right, and we will see that how these things work. All right, and secondly, the effect of this uncertainty in your message can be solved by some clever tricks, which we will actually show that for example, they can do some further discussions and or maybe some classical communication, but via that this idea can be actually used for our advantage. We will see that whenever we work out a specific protocol. All right, so what is the idea that we will talk about? So let's see. So the basic idea, quantum cryptography is a huge field, and as I already said, that there are many research areas where people are working on, but we will focus on a specific kind of quantum cryptographic protocol, that is quantum key distribution. Quantum key distribution. Okay, so what is the idea of quantum key distribution? The idea is you have two parties, let's call them Alice and Bob. All right, Alice will send some message, but it will be encrypted. Encrypted means that it's not readable, right? It will not make sense, and there is a key. If you use that key, then you can read it. All right, so it can be a string of qubits or something like that. All right, and what Alice wants to do is to distribute this key among Alice and Bob. All right, and if we can do that securely, then if this key distribution is done securely, then we can guarantee that our communication is secured from eavesdropping. All right. So there is a famous quantum cryptography, quantum key distribution protocol, which was invented by Bennett and Brassard in 1984. Okay, so that is why this is called BB84 quantum key distribution. Okay, in this video I'm not going to the details of this because I'll do it in the upcoming videos. So I'm just trying to give you the basic idea that they want to distribute a key so that whatever encrypted message Alice sends to Bob can use that key and read it. All right, so that's the basic idea. And now I can give you some general ideas. How can we communicate securely? That's the goal we want to set. I mean, that is what we want to achieve. Okay, how can we communicate securely? So one of the most ancient ideas was that you change each letter by 3 digits after it. So for example, A will be replaced by D, right? Similarly, B will be replaced by E. Then if you have a word like A, B, C, it will be written as D, E, F, and then there is no way you can read it, right? So this was one of the ideas like used in 1,000 years ago to encrypt messages, and that was sent by some carrier like a pigeon or some human. All right, but these days we have smart computers, and our computers can actually crack these codes, even if this mapping is not the same for everything, every letter. For example, A, if we make it random, for example, A goes to M and B goes to P, if it is like this, even if we have a mapping like that and it's 2 ways, if it is like that, still our computers can break it. Can you think of it like how is it possible? I would suggest you to pause the video here and think about it. How can you crack this encryption using a computer? Okay, take some time and think about it. And now I'll give you the answer. The answer is, in English language, not all the letters come with the same frequency. What it means is that, I mean, letters like R or A occurs more, and letters like X and Y occurs less, way less in a sentence or in a paragraph, right? So there are some standards. I mean, there are some analysis, and you can train a machine learning algorithm that I'm giving it some regular English letters, English paragraphs. It can actually analyze and say, for example, R occurs only 5% of the times. A only occurs like 3% of the times, let's say, for example, but X is like 0.001% of the times. All right. So by this analysis, you can actually crack that. Because if you see that 5% of the times you are actually getting, let's say, for example, M in that message, then you can kind of guess then that is R. And with some trial and errors, you can actually crack it in a few tries. Okay, whenever it makes sense, you can take that, and then you can see that the whole message is making sense. Isn't it amazing? I find it really amazing, and these are amazing ideas. Okay, so quantum cryptography is something really amazing, and if you really want to pursue it further, then I would suggest you to read some mathematics, say in particular number theory, then abstract algebra, group theory, and many more. I mean, like coding theory and computational complexity theory, those things. All right. So, okay, let me write it down. I think that would be better. And computational complexity theory. Okay, so if you are good in these branches of mathematics, then you can really work on front-end quantum cryptographic protocols. All right, so I want to give you one more idea, that is some general remark. So what are the remarks? Remark is, how does regular cryptographic protocols work, right? A public key crypto systems. Okay, how does these things work? So I think many of you already know that if I give you a number, let's say x, okay, if I give you a number, let's say x, and I say you to find two prime factors p and q, that means that p and q are prime numbers. Okay, so if I give you two numbers p and q, it's very easy to calculate x, right? You just multiply, even if it is like 100 digits long, and if it is 100 digit long, then you can just sit down and calculate in like a few hours. If you're really patient, that you can do that even by your hand, and with a computer it's not a big deal at all, right? But what if the other way around? I give you x and you find the prime factors. It is I mean, if you use all the known algorithms, and if you use all the classical computers in a cluster, all the classical computers that exist in the world right now in a cluster, and run this algorithm, if this is 100 digits long, okay, if it is 100 digits long, then you can prove that it will take like the age of the universe, 13 billion years to solve. Okay, this is one of the basic ideas of public key distribution these days. I mean, public securities, public key, or you can call it public key crypto systems. Okay, so the idea is, this is not impossible to solve, but it is extremely difficult to solve in any realistic condition. Okay, but so multiplying it, I mean, okay, let's write it like this. If you have p and q, and if you want to go to x, there are polytime algorithms. Okay, there are polytime algorithms. But if you have x and you want to go to pq, those are exponential time algorithms. Exponential time algorithms. Okay, but there are two catches. One is, there is no proof that there is no classical algorithm that can solve it in a polynomial time. So it is not proved. It is not proved that there is no classical algorithm there's no classical algorithm that finds the prime factors in polytime. Okay, so if there is someone smart enough to find it, then he or she can crack all the security systems in the world existing right now. Okay, but yeah, obviously it's not that easy. It's not that easy, but it's not proven that there's nothing. But in quantum computers, there exists an algorithm which is called Shor's algorithm, which actually does that in polytime. Isn't that fascinating? I mean, you can break, if you have a working quantum computer, then you can actually break all the classical security protocols classical security protocols existing in the world today in polytime, in less than a few days maybe. Okay, so this is the power of quantum computing, that you can know. But the catch is, if you have a working computer, then you can also build a security protocol that is not easy to break. Okay, and some of them are proven to be secured. Proven to be means that you cannot break it. Okay, so this is the idea, and we will talk about BP84 in more details in the upcoming videos. But I hope you enjoyed this idea, and if you really want to pursue this field, then I would say that learn those things that I mentioned in mathematics and learn about quantum computing more, and then you can jump into quantum cryptography. All right, I hope you enjoyed this introductory video, and we will get into more details in the upcoming ones. All right, thank you so much.